Hello all. I just realized that you're probably taking Unit 4 tomorrow, so I'm gonna try to quickly go through another past paper. And the inspiration is a question that the student asked in a different video. Okay, I think it was the video from October 2025. So the student asked the question about January 2020. Okay, so this is a very historic test now that I think about it, because it was right before COVID started, I think. So anyway, I'm gonna go through this over this quickly, because you're taking the test tomorrow and also I need to do something. So let's just dive in. So section A, question 1. A neutron can decay to produce a proton. Which of the following equations correctly shows neutron decay? And the correct answer is C, okay? And notice that the reason is that we have to conserve lepton number, and the lepton number of the electron is 1. Therefore, we need an anti-neutrino, which has a lepton number of -1, okay? Question 2. A distance d from a point charge of magnitude q, the potential is V. Which of the following is the potential at the distance 4d from a point charge of magnitude 2q, okay? So the voltage is kq over d, okay, for charge q. Therefore, the potential for the 2q charge will be k2q over 4d, okay? And this cancels, so we get v over 2 pretty much, right? And the answer is B, okay? Oops, sorry. And we'll probably not edit this video, okay? So I'm gonna try to be careful about what I'm saying and what I'm doing. So question 3, a ball of mass m traveling with velocity v strikes a wall at right angles. It bounces off the wall in the opposite direction at the same speed. Which of the following is the impulse on the wall? So, okay, the impulse on the ball is going to be delta p, right? So since the final momentum is in the opposite direction than the initial one, then delta p is, I recall that it's p final minus p initial. So we have minus mv, right? Because I'm using a negative sign for the final momentum. So the impulse of the ball is minus 2mv. Therefore, the impulse on the wall, which we are interested in, okay, see, we want the impulse on the wall, is the opposite of that. So 2mv, okay, so the answer is B. Moving on to question 4, the diagram shows equipotential lines about a point charge. Which of the following diagram shows a possible combination of electric field lines and polarity of point charge to produce this pattern? First of all, the voltage is positive, therefore it's a positive charge. And the only correct, okay, you can see that C and D are obviously wrong. And then B shows a positive charge with the electric field lines going inwards, which is erroneously wrong. So the correct answer is A. Question 5. The diagram shows a potential difference applied across two conducting parallel plates. Point X is midway between the plates. Which of the following is the electric field strength at point X? First of all, it doesn't matter where the point X is. It can be there, because the electric field is constant close to parallel plates, okay? So let me erase these dots. All right, and also the direction is downwards because we have to go, oops, what's that? Sorry. I need a pencil, okay. So the direction is downwards because we have to go from higher potential to lower potential. Okay, so it's either B or D. And recall that the electric field between parallel plates is V over D. And therefore we have 10 over 0.2 meters, which is 20 centimeters. And the answer is 50. So the correct answer is B. Okay. Now, question 6. A gamma photon of energy 18 MeV produces a particle and its antiparticle. Which of the following will give the maximum possible mass of the particle in kilograms? So we have to use our OG's formula E equals mc squared. So m is actually 2mc squared, sorry, because we produce two particles, the particle and its antiparticle, which have the same mass, right? So m is 18 MeVs, 1 MeV is 10 to the 6 EVs, 1 EV is 1.6 times 10 to the negative 19 kilograms. And then we have to divide by 2 times the speed of light squared. Okay, so first of all, A and B are wrong because the speed of light is not squared. And the correct answer is actually D, because 18 over 2 is 9, okay, times 10 to the 6 times 1.6, and so on. So the answer is D. Moving on to question 7. A current carrying wire is placed between two magnetic poles as shown. The magnetic flux density in the region between the poles is 0.07 teslas, okay? Which of the following gives the magnitude of the force on the wire in newtons and its direction? Okay, for the direction we have to use Fleming's left-hand rule, okay? Remember, our index finger has to point in the direction of B, and B goes from the North Pole to the South Pole, so your index finger has to point that way, downwards. And then your middle finger has to point towards the component of the current that is perpendicular to B, so this component, okay? Therefore, your thumb is going to point towards the direction of the force, which is, let me see, out of the page, okay? So it's either C or D, right? But, okay, so F is B-I-L. I promise to make better letters, so I will try. So F is B-I-L, and the component of the current that is perpendicular to B is given by cosine theta, right? I times cosine theta. So that's 0.07 times the current, which is 1.5, times the length, which is 5, so 0.05. And then the cosine of theta, by the way, the cosine of theta, the way I drew it is confusing. So this is the component we need. So this is the theta, okay? So cosine theta is 5 over 6.5, okay? So let me, wait, I'm confused now. Sorry, the length here is 0.065 and the cosine theta is pretty much 0.05. Okay, so this can also be written as 0.05 over 0.065. So you have to divide by 0.065. So this 0.065 goes away. And the correct answer is actually C. Okay. Yes, okay. Sorry, I got confused for a moment. Okay, question 8. Point charges of plus Q and minus Q are placed at X and Y respectively. When another charge is placed at Z, the resultant force on the charge at X is 0. Distance xy equals distance yz, okay? So let's call this distance D, so this is also D, and let's call the mystery charge Q prime, and we know that it's positive, okay? Why do we know this? Because the negative charge is going to attract the positive charge Q, therefore Q prime has to be positive to provide a force in the opposite direction, okay? So pretty much we have, let's write it in red, so K times Q squared over D squared, which is the force to the right, has to equal the force to the left, which is going to be K Q prime over 4D squared, right? Because we have twice the distance, okay? So d squared goes away, k goes away, q goes away, and q prime is calculated nicely to be 4q, which is answer D, okay? Question 9. The diagram shows the momenta P and Q of two bodies about to collide. When the bodies collide, they merge and move on as a single body. Which of the following diagrams shows the resultant momentum, okay? So pretty much you have to add up P and Q. So P and Q is the total momentum before, so Pi, right? So we have to add them vector-wise. So if we parallel transport, actually let me do it here. Let me erase this. If we parallel transport Q and put it there, okay, then we can just add, how do we add two vectors? We add the tail with the end, sorry, so the tail of P with the end of Q. So pretty much this is Pi, right? So is there anything that resembles that one? Yes, it's answer C. Okay, simple as that. Let's go to question 10. In an electron deflection tube, electrons are released by passing a current through a metal filament. What is the name of the process that releases the electrons? It's an easy one. It's thermionic emission. Okay, so it's one of the things that you should know for A-level physics. Right. We quickly move to section B and question 11. A section from the periodic table is shown. Okay, we have some elements and some atomic numbers, okay? And then technetium, Tc, is produced when a deuterium ion collides with a nucleus of one of the other elements shown in the table. In the process, a number of neutrons are also released. And as a Greek-speaking person, I have to say this. So technetium means something that is artificial, okay? It's the Greek word for artificial. Actually, artificial intelligence in Greek is called technidi, which is technetium, artificial. So technidi, noimosini, which is intelligence, okay? So technetium means artificial, and it's artificial because it is not observed. It's I think it's the only element in the periodic table that was never observed in nature because there is no mechanism to produce it, and its half-life is something like a few years. I don't know. Let me check actually. Okay, give me 1 second to Google this. Or maybe I should Google it with you. Okay, let's go Google this. Okay. So, let me see. Okay. Technetium. Okay, there it is. Let's ask half-life. I said a few years. Let's see. It's actually 6 hours. Okay, so even less. Okay, let's go back. So the question says, deuterium is an isotope of hydrogen with 1 proton and 1 neutron. Complete the nuclear equation to determine the element and the number of neutrons released. Okay, so deuterium has 1 proton and 1 neutron. Therefore, its mass number is 2 and its atomic number is 1. Okay, so to the left-hand side, we have 98 protons and neutrons. Therefore, we need 3 neutrons to balance the equation on the right-hand side. So a neutron has a mass number of 1 and an atomic number of 0, okay? And then to the right-hand side, we have 43 protons. Therefore, we have to have 43 to the left-hand side. So the only way to balance this is to have the element with 42 protons, which is, from the table, molybdenum, okay? And this is the balanced equation, and we can move on. Question 12. The following passage is taken from an article about the history of particle physics. Okay, mystery particle. By 1932, scientists knew of the existence of the subatomic particles, the electron, the proton, and the neutron. Okay, these were believed to be the fundamental particles, which was totally wrong, as history has taught us, okay? Anyway, in 1936, scientists were using tracks of cosmic rays to identify a predicted particle known as a meson. Instead, another particle was discovered, the muon. This was so surprising that Nobel Prize-winning physicist Isidor Rabi said, "Who ordered that?" So, describe how the underlying particles fit into the standard model. Okay, so the underlying particles, I'm gonna group them together in a way that will make sense in a moment. So, we have the electron, the muon, the proton, the neutron, and the meson. Okay, so quickly, what are the properties of the electron? Its charge is negative -1, and we mean minus E actually, okay? The lepton number is 1, okay, yes, it's 1, and it's a lepton, right? And it's a first generation lepton, and it's also a fundamental particle. What does fundamental mean? As far as we know, we cannot cut it into smaller parts, okay? Simple as that. The muon also has a charge of -1, okay? Lepton number of 1, okay? It's also a lepton, like the electron, but it's a second generation lepton, okay? Because they were discovered after the electron. And it's also a fundamental particle, meaning that as far as you know, you cannot cut it, okay? The proton now has a charge of +1, right? A baryon number of 1. It's a baryon, we just said it. And it consists of 3 quarks, okay? And the neutron has a charge of 0, baryon number of 1. It's also a baryon. It also consists of 3 quarks, Q, Q, Q. These are not fundamental, okay? Not fundamental. And actually for the proton, you can say that the proton is 1 up, and 1 down. And the neutron is 1 up, 1 down, and 1 down quarks, okay? Now for the meson, the charge can be 0 or ±1 because it's not specified what kind of meson this is. It can be a neutral pion, positive pion, negative pion, whatever, okay? The baryon number and the lepton number are 0 because it's a meson, it's not a baryon or a lepton, so it doesn't have baryon or lepton number. And it consists of a Q, a quark, and an antiquark, okay? Like just like every other meson. And this is the answer. And we are moving on to question 13. This is an old test by now. I mean, January 2020. It's already 6 years ago, which is crazy because this video is recorded on January 2026. Okay, and I keep saying sometimes in my videos that despite taking Unit 4, sometimes they ask questions from Unit 1 or Unit 2. Okay, so this is an example. Okay, so the photograph shows a jumping toy. The head is pushed down onto the base, compressing a spring. When released, the spring expands and the toy jumps into the air. A student investigated the toy. The student placed the toy on a balance to measure the force required to compress the spring. The force was 14 newtons when the spring was fully compressed by 1.7 centimeters. When the toy was launched, it jumped to a height of 1.5 meters. Show that the maximum energy stored in the compressed spring was about 0.1 joules. This is a Unit 1 question, and I'm going to show you actually. This is one of the techniques or strategies you can use in a test. Just go to the back of the paper and read the formulas. So let's see. This is what we need actually, okay? So this is the energy they are asking. 1/2 F, we are given F, we are given delta X, so you can find the elastic energy just by reading the formulas in the back of the paper, okay? You should be able to remember this anyway, but it's good to have in mind that sometimes they ask simple questions like that from Unit 1. So don't panic and check the back of the paper. So the energy, let's call it U, is 1/2 F times delta X. So 1/2 times 40 newtons times 0.017 meters yields 0.12 joules, which is about 0.1 joules. Okay, simple as that. Just by reading the back of the paper, you get 2 marks. Part B. Initially, the spring was fully compressed. As the toy was released, the head accelerated upwards on its own until the spring was uncompressed. The head then pulled the base upwards and they moved together at the same speed. Okay. The student used the elastic potential energy stored in the spring to determine the maximum speed of the head. Okay. The student used the gravitational potential energy gained by the whole toy to determine the initial upward speed. Determine whether the toy obeys the law of conservation of momentum using values of speed calculated in this way. Okay, this is a strange problem, the way it's worded, but let's start working on it. So this part, okay, this is kind of like the first question in this part B of question 13. So if we use 1/2 the mass of the head times the velocity of the head, which we are looking to find, if we set this equal to the elastic energy, which we calculated in part A, okay, just like the statement says, right? Then we will find that V head, and the mass of the head is 6.4 grams. Then V head, it is the square root of 2 times 0.12 over 6.4 times 10 to the negative 3. Remember that 1 gram is 10 to the negative 3 kilograms. Okay, so the answer is 6.1 meters per second. And while at it, we can also calculate the momentum of the head, which is simply the mass of the head times the velocity of the head. Okay, and if we plug in numbers, we find 0.039 kilograms times meters per second. Okay, let me use a clean page now to do the other part. Then this sentence, the second sentence, says the student used the gravitational potential energy gained by the whole toy to determine its initial upwards speed. Okay, so let's find the speed that way. So 1/2 mass of the toy times the velocity of the toy squared should be equal to the mass of the toy. Oops, let's call it mt, like we did. So the mass of the toy times g times h, where h is 1.5 meters. Okay, so this is the maximum height. So the mass of the toy cancels, and vt is nothing but the square root of 2 times g times h, and this is 2 times 9.8281 times 1.5, the square root, so 5.42 meters per second. So the momentum of the toy is going to be the mass of the toy times this velocity of the toy. So the mass of the toy is 7.2 times 10 to the negative 3 kilograms times 5.42. And this yields actually 0.039 kilograms meters per second. And notice that this is exactly the same as what we just found for the head. So actually momentum is conserved. Okay, so momentum conserved. All right. And now part C, determine whether the kinetic energy was conserved as the head began to pull the base upwards. Okay, so we can calculate the kinetic energy of the toy as p toy squared over 2m toy, right? And this yields 0.11 joules, okay? And this is the kinetic energy after, pretty much, okay? So the kinetic energy we start with is the kinetic energy of the head, which is P head squared over 2m head, which yields 0.12 joules. Okay, so kinetic energy after is less than kinetic energy before, kind of less. I mean, it's kind of conserved almost, okay? But okay, the problem states that, sorry, the mark scheme states that this is not conserved. Okay, let's move to question 14. A track for go-karts is being built in a park. The design criteria state that the track must have semicircular ends with straight track in between as shown. The track must allow the go-kart to travel safely at speeds up to 35 kilometers per hour, which is 9.72 meters per second on the bends. The mass of go-kart and driver is 185 kilograms. The diameter of the semicircular end is 30 meters. For one design, the track is horizontal, okay? As the go-kart goes around the semicircular end of the track, centripetal force is provided by friction between the track and the tires. This is shown in the free body diagram, force diagram below, okay? Show that this design meets the design criteria. The maximum frictional force is 1180 newtons. Okay, so we have to pretty much calculate the quantity. The centripetal force is going to be mv squared over r if the track the go-kart achieves that maximum speed. So it's going to be 185 times 9.72 squared, okay, which is the speed, over the radius, which is 15, right, because we're given the diameter. And if you multiply, you find 1,165.2 newtons, which is less than 1,180 newtons, which is the requirement. So this is going to work, okay? Part B. Second design uses a track that is banked at the semicircular ends. The track is banked at an angle theta to the horizontal, okay? At the particular speed v, the go-kart can follow the track without any frictional force perpendicular to its motion. The diagram shows the forces on the go-kart as it is moving away. Show that the tangent of theta is 2v squared over g d, where d is the diameter AB of the curved part of the track. So that's the normal contact force. Okay, so you have to imagine that the go-kart is moving away. So therefore, this is the radius of curvature. I mean, this is the radius, like the circular motion happens around the center of the track, which is there. I hope this makes sense. You can convince yourselves by using your hand going into the page, okay, or coming out of the page, and you will see that it undergoes a curvature like that. So the centripetal force is this one, okay? This is what I'm trying to say, okay? Therefore, we have to find the component of the normal, this component, the red component of the normal contact force, okay? So we can analyze the normal contact force into this component, which is perpendicular to the weight, and a component parallel to the weight, okay? So if this angle is theta, this is also theta, okay? The reason is because this line is perpendicular to this line, and then this line is perpendicular to this line. Therefore, the angles are equal, and that angle is theta. Okay, I'm gonna remove the green lines. Okay, let me remove it. Okay, remove them. All right, so what I'm trying to say is that this is n sine theta, and this is n cosine theta. N sine theta is the centripetal force, so it's equal to mv squared, and let's do it over r, but r is d over 2, okay? And then we also have an equation for the other component. And the other component is n cosine theta, right? And this is equal to the weight, which is mg. Okay, because there is no motion upwards. I mean, the cart is not moving in this direction that I just drew. Hopefully it doesn't move, okay? So if we divide this, n goes away, the mass goes away, and then sine theta over cosine theta is tangent of theta, right? And tangent of theta is simply 2v squared over gd, exactly as asked, okay? Then part 2, calculate the angle theta using the stated design criteria for this track. So tangent of theta should be 2 times 9.72 squared over 9.81 times d, which is 30, right? So theta is, let me use my calculator because for some reason I didn't write this down when I was solving the paper. I go over all papers, guys. I mean, I solve them myself without relying on the mark scheme because I want to have an understanding of what's going on, okay? So this is why it takes me some time to prepare these videos. So, okay, let me see. So the answer is 32.7 degrees, which is 32.7 degrees. Which makes sense. I mean, it's a reasonable angle, okay? If you calculated something like 90 degrees, it would be crazy, okay? Even though go check, back in the day, there was a show called Top Gear on BBC, and they tested crazy trucks that had angles of like 70 degrees or something like that. So go check them out. So let's move on to part C. A banked truck will cost more to build. Suggest whether there are any significant advantages that will justify the cost. Okay, so first of all, a cart will be less likely. Less likely to go off the track. So it's a safer option actually, okay? And also higher speeds can be achieved because we will have two sources of centripetal force, which will be the how is it called, the contact force plus friction. So it kind of worth the money, I guess. So moving on to question 15. In 1908, Rutherford, Geiger, and Marsden investigated the interaction of alpha particles with matter. In one set of experiments, they directed alpha particles towards a thin gold foil. State why the alpha source and gold foil were contained in a vacuum, and the reason is that air stops alpha particles. Okay, thus we need the vacuum. Okay, part B. At that time, one model for the structure of atoms was the plum pudding model proposed by J.J. Thomson. In this model, the positive charge and mass were spread evenly through the atom. Negatively charged electrons were distributed within the atom. Okay, discuss the extent to which the results of the alpha particle scattering experiments justified replacing the plum pudding model with a nuclear model of the atom. And I remind you that the plum pudding model suggested that the atom looked like this, and the blue is the positive charge, okay? So it's full of positive charge, and then you have Even though I put them as plus, maybe I can use crosses, okay? So the crosses are the plums on the pudding or the electrons, okay? So in a scenario like this, you expect alpha particles to just go through. And because there are equal forces on the alpha particles from this side, I guess, and this side, then the alpha particles will just go through. And with some of them being deflected, I mean, these ones will be deflected, I guess, because there will be the contribution from this side is less than the contribution from this side. I hope this makes sense, okay? So in the plum pudding model, you will see most alpha particles going through and some being deflected, but there's no chance to see particles backscattering, okay? So let me erase this and let's write the answer, okay? So most alpha particles will go through undeflected with some being deflected at really small, or let's say at small angles, okay? This can be explained away by both models. Okay, however, in the experiment, some alpha particles backscattered at angles larger than 90 degrees, okay? This can only be explained by the nuclear or Rutherford's model. Oops. Of the atom. Okay, this was question 15. Let's go to question 16. Some spiders may be seen suddenly moving up into the air even when there is no wind. This happens when they let out strands of web. The spiders are pulled upwards as the electrically charged strands of web interact with the Earth's electric field. The average strength of the Earth's electric field is 120 volts per meter downwards. State with a reason the polarity of the charge on the strands of web. So if the electric field is pointing downwards, that's the direction of motion of a positively charged particle. Therefore, since spiders move upwards, then this means that the strands have to be negatively charged, okay? So since E is downwards, then Q must be negative as E points in the direction a positive charge will move. Okay, question B. A spider moves upwards after letting out a strand of web. Determine the initial upwards acceleration of the spider. And they give you the mass of the spider and the total magnitude of charge on a strand of web, okay? So what are the forces on the spider? So if this is the spider, okay, it has its weight, pulling it downwards, and then it has an upwards force, Q times E, right? So Q times E. And since it moves upwards, this is the direction of the acceleration. So the equation that puts everything together, we have sigma F equals ma, with A pointing out upwards, which means that we can take QE to be positive. So QE minus mg equals ma, or A is QE minus mg over m. So do I need a clean page? I think so. So A is 3 times 10 to the negative 7 times 120. So this is the charge, this is the voltage, sorry, the electric field, minus 3 times 10 to the negative 6 kilograms, which is the mass, times 9.81 over 3 times 10 to the negative 6. And if we do this calculation, we find 2.2 meters per second squared, okay? Which is the acceleration of the spider, I'm sorry. Okay. Part C, the Earth has an electric field because charge is distributed over its surface. Determine the quantity of charge of on 1 square meter on the Earth's surface, which would cause an electric field of 120 volts per meter. You should assume that the charge is distributed evenly, okay? So the best way to think about it is to think of the Earth, okay? And the radius of the Earth, okay? So this is a sphere. What's the electric field of a sphere? Q over 4 pi r squared, right? So first of all, you can find the total charge. So Q is 4 pi r squared times the electric field. Oops, I forgot the K. Silly me. So KQ over 4 pi r squared. Therefore, we have to divide by K, right? So let's use a clean page. So Q is 120 volts per meter times 6,400,000 meters, which is the radius of the Earth squared, over K, which is 8.99 times 10 to the 9. And the charge is 546.74 times 10 to the 3 coulombs. Okay, now this charge is distributed over the whole surface of the Earth. Okay, so Q over 4 pi r Earth squared will be 546. We need to calculate this, I mean, okay? So 546.74 times 10 to the 3 coulombs over 4 pi times 6,400,000 squared yields 1.06 times 10 to the negative 9 coulombs per square meter. So in 1 square meter, so 1 square meter has 1.06 times 10 to the negative 9 coulombs of charge, okay? Which is not a lot. I mean, it's not a crazy number. And this was question 16. Now question 17, okay. Again, question 17 involves some knowledge of unit 2 this time, okay? So a student is designing a night light for a child. When switched on, the night light should come on brightly and its intensity should then gradually decrease to 0. The time taken for the light intensity to decrease to 0 should be as close to 10 minutes as possible. But the time must not be less than 10 minutes, okay? So the diagram shows the student's design, okay? The student uses a light emitting diode, LED, and a resistor R. The LED stops emitting light when the potential difference across it falls to 1.4 volts. The student assumes the LED has a constant resistance of 340 ohms. Capacitance with the following capacitances are available, and they give us a list. Determine which capacitance the student should use, and they give us the resistance R, this one, okay, which is what is it, 860 ohms. All right, so first of all, we'll have to find the current in the circuit, okay. So 12 volts is I times R plus the resistance of the LED. So the current is 12 over 860 plus 340. So the current is simply 0.01 amps. And we did this to find the voltage, the initial voltage across the LEDs. Okay, so the V of LED is simply I times the resistance of the LED. So this is 0.01 times 340, so 3.4 volts. All right, let me use a clean page. So now comes the harder part. So voltage is equal to the voltage across the capacitor the voltage across the LED should fall like the voltage across the capacitor, following the rule V equals V naught E to the minus T over the time constant. Okay, so E to the T over the time constant should be V naught over V. So T over the time constant should be equal to the log of V naught over V. So tau, so the time constant, this was a difficult problem. So the time constant should be T over the ln of V naught over V. So remember that T is nothing but RC, right? So I'm just going to write that T is T over R, but which R? The total R across the whole circuit. And then ln of V naught over V. So C is, the time is 10 minutes times 60 seconds. The total resistance is 1200 ohms. And then we have ln of 3.4 over 1.4, which is what they tell us, okay? And this calculates to 0.56 farads. Therefore, we need to use this capacitor, the 0.58 farads. So use the 0.58 farads so that it doesn't take less than 10 minutes to go. Less than 10 minutes for the light to switch off. For the light to switch off. Okay. Let's move on to part B now. In practice, the resistance of the LED does not stay constant. The graph shows how current varies with potential difference for the LED, okay? So if we plot, remember Ohm's law, which does not really apply for LEDs, but let's write it down anyway. So R is V over I. So if we plot I versus, so I is, what is it, V over R, okay? So I'm trying to say that the gradient of this curve, so the gradient is 1 over R, okay? And you see that as we approach 1.4 volts, the gradient decreases, therefore the resistance increases. Okay, hope this makes sense. So as I'm gonna write it like this, as voltage, decreases, not increases, I'm sorry. So as voltage decreases, the gradient also decreases. Therefore, the radius, why do I say radius? The resistance increases. Okay, so if R increases, then T, the time constant, which is equal to RC, also increases. So it will take longer for switch to for light to switch off. Okay, and now part C. The student states a capacitor is being used in this circuit. The function of the capacitor is to store electric charge. Explain why this is not a complete description of the function of the capacitor. So the overall charge something's wrong. Okay, so the overall charge in a capacitor is 0 as the positive and negative charge are separated. And they are equal, right? I mean, you have as much positive as negative charge in a capacitor. So the capacitor stores energy, actually, which is then released in the circuit. So the capacitor is sort of like a battery that doesn't unload all the charge immediately, okay, like a battery does. So that's the function of a capacitor in a circuit, pretty much. Okay, question 18. The photograph shows a demonstration AC generator used in a school. Okay, so I think what's going on here is that this guy rotates this way, okay? So the coil sometimes has its whole surface parallel to, so the magnetic field points from the North Pole to the South Pole. So as the coil rotates, it shows its whole cross-section to the, its whole cross-section cuts the field or is parallel to the field. When it's parallel to the field, there is nothing going on. But when it's perpendicular to the field, you have EMF produced, okay? I hope this makes sense. So the handle is used to rotate the coil between the magnetic poles. When a light emitting diode LED is connected across the coil, the LED flashes on and off as the coil rotates. Explain this observation. So the coil cuts through B, the magnetic flux density, as it rotates. Okay, so EMF is induced, and because we have a closed circuit, current runs through the circuit. Okay, when the coil sides switch position, the current direction changes. In other words, if the coil is like this, and this is the one side and this is the other side, when it rotates, the sides will change side, if this makes sense. So current is going to flow this way or this way. Okay, so because the LED allows only one direction of current, to go through, it flashes. And this is the answer. I mean, this is a complete answer, I think. B. The output potential difference V for the generator is recorded using a data logger, and a graph is produced of V against T. Add to the graph to show the output if the angular velocity of the generator coil is halved. So, the induced EMF is proportional to the change. So it's proportional to NB times the change in the area, right? I think I went too fast. So E is N d phi over dt. But remember, this coil rotates inside these magnets, right? So the cross-sectional area shown that cuts through the field changes at all times, right? And it changes according to how frequently you rotate the coil, I guess. Okay, it changes with the frequency pretty much. Or in other words, this is proportional to N times B times the area times the frequency. Okay, so it says add to the graph to show the output if the angular velocity. Okay, so omega is 2 pi f. So if we halve the angular velocity, we're going to halve the maximum voltage, right? And we will also increase the period, right? So what I'm trying to say is that if, let me use a clean page, if f prime is f over 2, then the new period is going to be twice the old period, and the new EMF is going to be half the old EMF. Okay, so if we go to this graph, we use blue, so we see that the maximum EMF is about 5, so this is going to be the new EMF, the new maximum EMF, so it's going to be something that looks like this. Okay, I hope this makes sense. Oops, so it should go there. Okay, let me erase this. So, okay, this, and then again this. Okay, something like this. So half and then twice the period. Okay, half the amplitude, twice the period. Okay, and then in part 2 they ask the same thing for some reason. So explain the changes in the graph when the angular velocity of the coil is halved. So E prime is going to be half the initial EMF, and also T prime is going to be twice the old one. Okay, and let's move to part 3. The coil rotates in a uniform magnetic field at the original angular frequency. The average magnitude of V is 3.2 volts. Determine the number of turns in the coil, and they give you the magnetic flux density in the cross-sectional area. Okay, so this problem is a little bit weird in that you have to think like this. So they give you the average magnitude of V. Okay, so if you think about the situation, if this is the magnet, the coil looks like this and it rotates in this direction. Okay, so in 1/4 of a period, so t over 4, it's gonna be, if this is the direction of B, in 1/4 of a period, it's the coil is gonna point in the same direction as the magnetic field, therefore there will be no change in flux, if that makes sense. So in 1/4 of a period, we will have the average magnitude of V, if that makes any sense. So E, the mth, is going to be the number of turns times the magnetic flux, which is B times A, over 1/4 of the period. And the 1/4 corresponds to this fact that I just said, that mth is produced only when the coil is perpendicular to the magnetic flux, okay? To the magnetic flux density B, okay? So we are interested in N, so we have to do E times T over 4 over B over A. And if we plug in numbers, we have 3.2 times 0.2 seconds. The period, you can find it from the graph. And you see that one period is 0.2 seconds, okay? And then we have to divide that by 4, which is 1 over 4 is 0.25. And then divide by B, which is 0.083 Teslas. And then A is 0.0048 square meters. So this gives you 401.6 turns, which is about 401 turns. Okay, and that's the answer. Okay, and now question 19. The student who asked me a question on the January 2020 paper asked me a question from the, question 19. Okay, so the question was about problem 19. So anyway, so the first cyclotron was created by Lorentz in 1931. Lorentz obtained an expression for the time t for a particle of charge q and mass m to complete a circular path in a uniform magnetic field of magnetic flux density B. The expression obtained by Lorentz is that one. Derive this expression. Okay, so when a particle moves inside the magnetic field, it undergoes circular motion, okay? So QVB is the force it experiences, and because its velocity is perpendicular to the magnetic field, to the centripetal force, this is equal to mv squared over r, right? So this velocity cancels. So we have QB equals to mv over r, but in circular motion, we can substitute v for omega r. So QB is m omega r over r, so r goes away, and then omega is 2 pi over t, so I'm gonna need a clean page. So QB is what is it, m times 2 pi over the period or the time needed. Okay, so t is 2 pi m over b q, which is exactly what they ask us to find. Okay, part 2. In Lorentz's cyclotron, an alternating potential difference was used to accelerate particles to high energies. Explain the significance of the expression obtained by Lorentz to the operation of a cyclotron. Okay, so T is independent of V, okay, of V, I mean the velocity. So it's a constant, right? And if we use an AC voltage, an alternating voltage, with frequency equal to 1 over this time, and notice that the time only depends on the mass of the particle B and Q, okay? All these things are constant, okay? So if you use an AC voltage with frequency 1 over T, then the polarity of the AC will change right when the particle exits the D's. So it will always be accelerated. Let me check out my answer in my notes. So, okay, that's the answer. Now let's move on to part B. In a cyclotron in which Lorentz expression applies, protons were accelerated to a speed of 1.5 times 10 to the 7 meters per second. Determine the time taken to accelerate a proton to this speed from rest. They give you the magnetic flux density and the accelerating potential difference. Okay, so first of all, we can find the time needed for one full revolution. Okay. Actually, no. Let's actually, since we are given the kinetic, the speed, let's calculate the kinetic energy, which is simply 1/2 mv squared. And these are protons, so you can find their mass over here, 1.67 times 10 to the negative 27. Okay, so if you plug in numbers, you will find 1.88 times 10 to the negative 13 joules. Okay, so the accelerating potential will give the protons an energy of Q times V, which is E times V, which is 1.6 times 10 to the negative 19 coulombs times 13,000 volts, and this is 2.08 times 10 to the negative 15 joules. Okay, so the number of revolutions can be found. I mean, how many revolutions did it take for the proton to go around until it acquired this speed? You can calculate. So you can divide the kinetic energy. The number of revolutions can be calculated by dividing the kinetic energy it acquires with the constant acceleration. I mean, the constant energy gained in each revolution from the voltage. Okay, so if you divide these numbers, you will find 90.38 revs. But remember that we have to divide this by 2. Why? Because, let me see if I can justify this. Because it gets accelerated twice, right? Because we have to account for the fact that, we have to account for the fact that it undergoes half a revolution, right? And then it gets accelerated. So let me write it down. Maybe it makes sense. Maybe I don't make sense. So these are the D's, right? And this is the AC over here. So let's say that the proton went this way, okay? So it undergoes half a revolution, and then it gets accelerated here. Then it undergoes half a revolution, right? And then it gets accelerated this way, and so on. So we have to divide this by 2. So this gives us, I actually haven't done it, so let me divide. So 90.38 over 2, 45. So actually I have the clean page, so we need 45.19 revolutions. Okay, so the time for one revolution is T is, what was the formula? 2 pi m over BQ, so 2 pi times the mass of the proton, which is 1.67 times 10 to the negative 27, over B, which is, what is B? 1.6 and then the Q is 1.6 times 10 to the negative 19, and this will give you 40.98 nanoseconds. Okay, so the total time will be 40.98 nanoseconds times 45.19. So this should be, let me see, 45 times 40.98 times 10 to the negative 9. So 1.85 microseconds, which is kind of fast, very fast actually. Okay, this is the answer. And part C is the last part, explaining why high energy particles are required to investigate the structure of nucleons. Okay, so the answer is, remember that the kinetic energy is p squared over 2m. So as the kinetic energy increases, p increases, but lambda is h over p, right? The de Broglie wavelength of a particle. So as p increases, lambda decreases, and lambda must be similar to the size. I'm gonna move to the clean page, to the size of a nucleus. Okay, so what I'm trying to say is that if the momentum of a particle is really, really high, its wavelength is going to be really, really small, and it's going to match the radius of the nucleus. Therefore, the particle in the nucleus can undergo diffraction phenomena and so on. Okay, and this was the January 2020 paper, Unit 4. I hope this is useful. I'm sorry I kind of rushed it, but I think you guys need this now because you're taking, so this is January 11 of 2026, and I think the test is taken tomorrow. Okay, so hopefully it's gonna reach people who need it. Let me know what you think about these videos. Please like, because it really helps with visibility. Subscribe, tell your friends, and so on. So see you in the next video. Bye.